Yours has love, so it has to be right, huh? They look like they're all the same.
Yeah.
Cool. I know, right? That's really exciting. I love it. I love it. So, okay, so let me write it down just so we have it written on here as well. So somebody hold it up so I can see. Thank you. So F is equal to E. And just so that I understand, that you really understand, how are F and E the same? How did that work? Go, Caleb.
All right, so each wave weighs 12 newtons. So for F, it has a radius of 2 meters.
Okay.
Take 2 times 12, you get 24 torque, I guess, going down. So you need force to apply up to be 24 because it only has a radius of 1.
On which one? On F?
F, yeah.
Do you mean on?
No.
Has a radius of 1? Oh, I see what you're saying. Okay, okay. I'm just a little slow. Gotcha. Okay.
And then you can kind of say the same thing for E. E is 12 times 1, so you have 12 torque going down. So you need somehow to get enough force going up so it equals 12 torque. So you need 24 times 0.5 to get that goal.
Does that make sense? What are the units of torque, by the way?
Newton meters.
Newton meters. Yeah, yeah. Okay, so you had F and then E, and then what was next? C is less than F and E. And then what was after that?
Yeah.
Oh, okay. We're gonna right. And then at the end was B. All right. And any other issues or questions? Like, how did it go? Do you feel like you understand why? Is there any issues or any discrepancies that we had there? Are we good?
I just have a hard time visualizing it, but I have to do the math.
Me too. It's all ratios, right? Yeah, I mean, it's not something that's necessarily going to be obvious. Like, well, duh, right? And I think that's actually, the fact that you said that like that is really true for most of this rotation stuff. I had a conversation this summer, actually, when we were talking about this big change and the fact that rotation is a big deal for this class. It's never been a big deal in AP Physics before, this rotation stuff. And one of the things that one of my colleagues said was, it's funny because translational motion, right, like 1 or 2 dimensional motion where you're like moving things, we can imagine that really, really easily. We understand that because that's the world we live in, right? We move from one place to another. We don't do a lot of this rotational stuff. That's not something we experience every day in our life all the time, right? Unless, like, you're talking about riding on a merry-go-round or, like, talking about something, like, that just doesn't happen a lot. And so I think that the thing that you have to remember is that all of the concepts are the same. We're just looking at it in a different way. Yeah. And that it's okay to do a little math. Yeah. And to not have it, like, be a totally intuitive, innate thing. That's okay. Yeah, yeah. Because you guys know how to do math. Or ratios. Like, that's not hard stuff. Okay. So life is okay? All right. So the next set of conversations that we're going to have today is all about kinematics. Yes! We've done kinematics before, right? You understand kinematics. We spent a lot of time doing kinematics last semester. What does the word kinematics mean to you? Yeah, describing motion, okay? Now, there is one little difference here, and that is that the kinematics that we're going to talk about now is rotational. Okay? Yes. All right.
Radians are always the best students.
They are. That is where we are going now, yes. So the game is here.
Radians are so hard.
I think it's an okay score, right? It's just that I feel like his writing is like super choppy. With all the commas.
All right, here we go. Let's do physics, not whatever Dostoevsky you're talking about. All right, here we go. So kinematics. We talked about kinematics a long time ago. We've defined all this stuff. You know how to do this. Okay? We're just defining it in terms of a little bit of different things. When we were talking about translational stuff, we definitely talked about displacing something, right? How far something's moved. And we usually did that in terms of like some sort of like maybe delta x, right? Some displacement, change in position from one place to another. All right, displacement over here. Okay? When we talk about it in terms of rotation, instead of saying a delta x, some distance that we can measure like with our tape measure in that way, we're going to measure it in terms of an angle. Yeah, that's all we're doing. So we're going to write it in terms of delta theta. Okay? Generally, the angle is measured counterclockwise. Generally, it's measured from the x-axis. Not always. It doesn't have to be. It's kind of like where do you put 0 when you're measuring this translational stuff. Okay? It's the same kind of question. But delta theta is the angle that we measure when we're talking about rotational kinematics. Okay? The units in translational displacement, the units were meters. Yeah, we should know that, right? Yeah. So whenever I ask those, you can like say them in a resounding way because you know the answer. The units for this rotational displacement are what? Now you're excited. Say it again. What are we going to measure it in? Radians. Yeah, we're going to measure it in radians. You can measure it in degrees, okay? But generally we use radians because radians are superior when it comes to rotational motion.
The truth is revealed.
Here's the deal. The beauty of the radian. Let me tell you a couple of reasons that we like the radian. We like the radian because it's a simple ratio, right? You guys have all heard radians before. Is that true? Has anybody not heard radians? Okay, good. So we've all heard it at some point. So a radian, so you should know this, but just to make sure that everybody's on the same page. Radian just comes from the word ratio. You know this, right? And a radian is just the ratio between the arc length and the radius of a circle. You know this, right? Okay? So the beauty of it is that it's just a nice little ratio. There are no units that go with it. A radian just says it's the ratio. Okay? Because this is in meters and this is in meters, so this really doesn't have any units. So you can just pretend the radians don't exist. We're just measuring an angle. Is that better? Does that make it a little bit better? Okay? Yeah. We know if you get all hung up and you're like, I need the degrees thing, we can always keep in our brains that 2 pi radians are how many degrees? 360. 1 full rotation, right? So if you get confused and you need to go back, you can do that. You're allowed. But know that everything that we're going to do in rotational is going to be in radians. So you can either convert and then convert back, or you can just kind of suck it up and do it. And know that it will be okay. I promise. And I'll help you if you have questions. I think sometimes people just get hung up on it because they get scared of it, and really you just need to, it'll be fine. It's just a nice little ratio. Life is okay? Yeah? Yeah? Okay. All right. There's and to be really clear, there is a difference, right, between the translational displacement and the rotational displacement like we saw in here, right? As these things are moving around, the one far out has a much bigger translational displacement than the one that's close in, but their rotational displacements they're the same. Yeah, so it's kind of interesting. After we talked about displacement in our conversation about translational motion, what was the next thing we talked about? Remember? So we talked about displacement. We took the derivative of displacement versus time. We talked about the velocity. And velocity was marked with a v. And v was delta x over t, right? We can do rotational velocity as well, or rotational angular velocity is sometimes what we call it. Angular velocity is marked with another Greek letter. It's the Greek letter omega. Say it with me. Omega.
Omega.
Omega. That is not a W. It is not a curly W. It is not the thing that looks like a W. It is the letter omega. It's the very end. It's the very last letter of the Greek alphabet. Okay? So if you were going to spell it out in Roman letters, it would look like this. Omega. And omega is just like, it's the same process. We're just going to take delta theta over t. No big deal. Is that okay? That's all we're doing. All right? Every single point, every single one of these weights on the rotating surface has the same omega. Does that make sense? Can we say that again? Every single point on this surface is covering the same amount of rotational displacement, right? Sweeping out the same angle in the same amount of time. Same angle and same time. If the top and the bottom are both the same, that thing's got to be the same also. Is that okay? Yeah? Okay, so that might be something you want to write down because that's kind of important. Here we go. So all points on what they call, when we're talking about things that are rotating, you have to be a little bit careful because you don't want to talk about things like fluids, like something full of liquid or full of a gas, because then, whoa, things get really weird really fast, okay? But if you have something that's not, it's solid, so it's not going to like flow, we call that a rigid body. All points on a rigid body will have the same value of omega because they're all going around that same common point. The units for translational velocity are? That's right, we know that one, right? Translational just means like our normal, like moving in a straight line kind of deal. That's meters per second. This rotational business, what are the units going to be? Take a look at it.
Radians over time.
Yeah, and what's time measured in?
Seconds.
So it's actually just what?
Radians per second.
Radians per second. I said that this is sometimes called, I'm just going to write a couple more notes here. Rotational velocity. Sometimes you'll see it called angular velocity. And just a heads up, I just told River that radians really don't mean anything, right? They're just kind of a placeholder, because remember, radians, it's just a ratio, so there's really no unit. And so if you get rid of the radians, then you just have 1 over seconds, which is just a measure of frequency, right? Does that make sense?
Yep.
Okay. How often is something going around? So sometimes they call it angular frequency. To confuse small children. Yeah. But now they won't confuse you because you know. Right? So it'll be okay. Is that okay? Or does that make sense? Usually you'll see angular velocity or rotational velocity, but I just wanted to give you a heads up that that may occur. Are we okay so far? No minds blown, right? This is not a big deal. We got this. All right. I want to try a problem real quick. I think you should know the answers to this one pretty quickly, but I'm going to let you read this individually, and then I'll let you discuss it in just a moment. Who has a greater linear speed?
The outer child.
The kid, the horse child. The horse, that's creepy. The child sitting on a horse? Yes. Which child has a greater angular speed? Neither. Both, yes, is the answer, right? They have the same angular speed. Life is okay? This is not hard stuff, friends. You can handle it. I know you can. All right. You do displacement, you do velocity. What comes next? Acceleration, right? Like, this is just obvious. We got this. Whoa. That was frightening. Let me make this normal sized again, shall we? Sorry, hold on just a second. Whoa, that's the problem. That looks better. Let's make it a little smaller even. There we go. Acceleration is marked with an A. Regular acceleration is marked with an A, and it is equal to what?
The display velocity over time.
Yeah, but it's not just plain old velocity. It's because if the velocity stays the same, then we have no
Angular
acceleration. It's a change, right? Yeah, so Jonathan doesn't get to talk anymore, not because I don't love him, but because he's answering the questions for everybody. Is that okay? Because I want to make sure everybody else gets to play too. So acceleration is change in velocity over time. We know that. So we're going to do the same deal. Do you see the parallels that are happening here? It's like the same thing. So acceleration is going to be marked, angular acceleration is going to be marked with an alpha. That's the very first letter of the Greek alphabet. So it's not a fishy, and it's not the A thing. It's what? Alpha. Okay? I really want to, like, it's not hard. Alpha. And alpha is, what do you think? What do you think it's going to be? Take a look. Change in what? Change in omega. I was supposed to do this in blue. I'm sorry. Yeah, change in omega over time. Is this okay? It's just different letters, but it's the same idea. So now this is talking about, like, if I give this thing a push, is it going to, whoa, hello. Is it going to stay at the same rate of spinning the whole time? No, it slows down, right? That means that my omega is going down, which means that my alpha is what? Negative, right? It's slowing down. It's the same thing. Slowing down. This one's slowing down in the rotational, right? So it's getting slower and slower and slower as it goes in a circle, as opposed to getting slower and slower and slower as it goes in a straight line. That's all we're talking about. Life is okay? Units here are what? Yeah, they are. Okay. No problem? Ready to play with this a little bit and make sure it makes sense? Okay. All right. I've got a couple of, this is a lot of words. I wanted to make them big so you could see them. So it's 3 questions. This is the first one, and then these other 2 relate to these choices, so that's why I wanted to make sure you could see it all on one page. I apologize for the fact that it looks really intimidating. I hope it'll be okay. So I'm going to turn the front lights off so you can see it a little bit better. I'm going to give you a few minutes to work on this individually, and then we'll discuss. Sound okay? Go. Jason, can you guys see that okay back there? Yeah. Okay. On like what they're saying here. So it's starting out somewhere, right? And it's ending somewhere. So these are like the initial and final positions. Is that okay? So let's kind of talk this through and make sure this makes sense. Because sometimes the way that they have these things written is a little bit funny. So for A, if we start on our unit circle, here's 0, right? Where is 3 radians? Where does that exist?
A little bit above the other 0 circle.
A little bit, well, 3 is almost 3.14, right?
Yeah.
And how many radians is this?
3.1.
3.14. So it's going to start like here-ish, right? So it's going to start here-ish. So this is the initial position. And then it's going to end at 6 radians. Where does 6 radians exist?
A little bit below 0.
Right? Because this is like, so 2 pi radians. So that's going to be a little more than 6. A little more than 6 than this one was. So it's going to be like over here. Something like that. Okay? So that. So if I'm attempting to draw an angle here. This is not working out super hot, but you get the idea. So that's the angle in A. What about for B? Where does -1 radian exist?
It starts going clockwise.
Yeah, so it's going to start somewhere below the x-axis, right? Yeah, so somewhere like here-ish. Well, no, like where there-ish probably, huh, right? Is that about 1? Okay, so that's going to be the initial point. And where's it going to end? Up above the x-axis, the same amount, right? So something about here-ish. So that's the angle for B. And for C, it's starting at about 1 radian, so somewhere around here. And it's ending at 5 radians. Where's 5 radians exist?
Close to the -1.
Close to like -1 radian? Is that what you
Yeah,
meant?
I was just saying, like, looking at the other one.
Like close to this one?
Yeah.
Yeah. Does that make sense? Yeah, because this is going to be how many radians?
3 pi.
Come on, friends, you know this. This is how many radians? Pi. This is how many radians? Pi over 2. This is how many radians? 3 pi over 2, right? So that's like 1.5 times 3-ish. So it's going to live somewhere over here, right? Because it's going to be somewhere between that and this. Yeah, and it doesn't have to be perfect, but it's going to be somewhere over here. And if you know that, and that's this one, again, not really good at drawing circles, but you get the idea. That's my angle here. Which one of those is bigger than 180 degrees? It has to be C. Is that okay? Now, did I have to draw that out in order to figure out that that's what it needed to be? How can I think through it without drawing out pictures? What can you do, B?
Well, you can just look at C and see how the difference is 4 radians and 4 is greater than pi.
Exactly. Yeah, like that's not, and I don't mean that in like a duh sort of way, but delta theta here is 4 radians. 4 radians is greater than pi radians, and pi radians is 180 degrees. Yeah.
So when you say 4 radians, you can't write that as just 4 pi, because they're 2 different things?
They're 2 different things, yes. So pi is a number of radians. And it's the number of radians that you get if you go over to here.
Yeah.
180 degrees. Yeah. Does that make sense?
Yeah.
Okay. That's a good question. Because sometimes we get them confused, right? Because we talk about pies and radians a lot, like in the same sentence, in the same breath.
Okay.
Yeah, does that make a little more sense to you? Okay, good. Okay. So now that we've got number 1 figured out, number 2 says suppose that the change in angular position for each pair of values above occurs in 1 second. Which choice represents the lowest average angular speed? So, just kind of thinking this through, angular speed is marked with what letter? Omega. And omega is delta theta over time. Can we figure out what delta theta is in each of these cases? Yeah. What I want to do right now, because you all did not agree on everything for the last couple of questions, I don't think. I want you to go back through number 2 and number 3, make sure that you agree with your answers, and if you change them, if you need to change them, change them. Okay, I'm going to give you like a minute and a half go, and then we'll check them. I'll give you some more space here. Question?
So in the third part, they're
Yes.
still doing it in 1 second, right?
Let me read it again carefully. If the object starts from rest at the initial angular position and moves counterclockwise with a constant angular acceleration and arrives at the final angular position at the same angular speed in all 3 cases. I think it's in the same time.
Okay. Just checking.
That's how I would interpret it.
Okay.
Yeah. Let me see him. Come on, David, let me see it. Boards up, let me see. No commitment back there. All right. Looks like you all agree on number 2. Suppose that the change in angular position is the same. So all you're doing is delta theta, right? Over delta t, which one has the smallest delta theta? It's got to be the same deal, yeah? Okay. To do this last last one, I'm going to pause for a minute. I'm not putting it off. I want to write something down. I want to show you some beautiful parallels that exist. All of these things are the same. You agree? Yeah? Here we go. We had some equations, right? Some kinematics equations that we established in our previous existence. Like, I don't know, VF equals VI plus AT. There is a very, very similar rotational equation. The rotational equation that matches looks like this. Omega F equals omega I plus alpha T. Oh, that looks pretty similar, doesn't it? Every time you see a V, you're going to put in an omega. Every time you see an A, you're going to put in an alpha. Okay? Let me give you two other equations. X equals VIT plus 1/2 AT squared. That was your favorite one. Right? And then there was another one, VF squared is equal to VI squared plus 2A delta X. Why don't you write the rotational equivalents for those two? Once you've got them, check with your neighbors and make sure they agree with you. All right. Did you get one, Jason? What'd you get for that first one? Or the, yeah, second one.
X is equal to omega initial times
Uh-huh.
plus 1/2 alpha times squared.
I agree with almost it. I didn't include that X because it's not going to be X anymore. What's it going to be?
Radian. Theta.
Theta, yeah. But other than that, lovely, perfect. Chris, did you get the last one?
Yeah.
What'd you say?
Omega final squared
Uh-huh.
equals omega initial squared
Uh-huh.
plus 2 times alpha
Yeah.
times delta theta.
Yeah. Now that you know that, go back to that question. See if you can figure out the answer. I think that will help. You know the initial omega and you know the final omega, and they're the same, aren't they? Yeah. So now that you know that, you know theta, so you should be able to find alpha and compare the alphas. Do you see what I'm saying? Okay. Oops. So this is omega final squared minus omega initial squared is equal to, I just moved the omega over just to be really clear there. 2A or 2 alpha delta theta. So can you solve that for alpha? Yeah? So what's your answer going to be? For number 3? Why is it B? David, why did you say B?
What?
Why did you say B?
But
Probably
Oh, who said it?
more.
Caleb said it. Caleb, why did you say B? You just throw your voice really nicely in this kind of general direction. Go ahead.
Because if the omegas are the same, if you rearrange it correctly, for it to like study that, I think the acceleration has to be the greatest for it to like equal all the others, or like I don't know, like where it's like stay like in ratio with the rest of them.
Mm-hmm.
The acceleration has to be the greatest.
Right. Does that make sense? Okay. So the bigger the theta, is that okay? The smaller the alpha. That's what we're saying. Life is good? All right. I'm going to throw something else at you. Here it comes. Oh, man, I thought I was done with graphing Miss Carveling. Oh, no, you're not. Of course not. But, friends, remember that this is very, very similar. It's all the same stuff, right? So in your head, whenever you see an omega, if you're just trying to figure out what to do, you can think, oh, that's kind of like a what? It's like a velocity, right? And if you see an alpha, you can think to yourself, oh, that's really kind of like acceleration. So here's a situation. I've got a graph of a changing omega over time. And I want to make a angular acceleration over time. I know you can do this. Do it right now. Go, go, go. Have a conversation. Write it down on your board. If you want to write it on your paper, great. That's fine too. I'm going to give you just a couple minutes to try that out. It's not going to be curves. I would concur. It's
To me, horizontal lines.
horizontal lines. Oh, that's even more descriptive. Make sure that everybody at your table understands and then draw it on the board so I can see it. This one's a little bit deeper. Yes! All right, so here's the situation. We've got a pulley with our little mass on it, right? It's so cute. It's the same mass that we saw before, I think. There's the clip art. All right. A weight is tied to a rope that is wrapped around a pulley. Okay, we're going to start to love the pulleys. A pulley is initially rotating counterclockwise, pulling the weight up. The tension in the rope creates a torque on the pulley that opposes the rotation. The weight slows down, stops momentarily, and then moves backward, but moves downward. Okay? Part A asks you to graph the angular velocity of the pulley. So this thing is rotating. You with me there? Okay? Graph the angular velocity versus time for the period from the initial instant when the weight from the initial instant shown until the weight comes back down to the same height, and then graph the angular acceleration. Go. You can talk about it. You don't have to do this on your own. I want you to figure it out together. And it's kind of interesting because I'm hearing a lot of you making good connections between this translational business and the rotational business. And that's what I want you to do because that's the best way to get what's going on here. So this thing, let's just make sure we understand what's going on. This thing is going to roll up, but it's not going to stay at a constant, right? It's slowing down, and it's coming to a stop, and then it's going to start speeding up going the other way, right? We are calling that first rotation counterclockwise, and we call that a positive or negative? Positive. It's positive, right? Counterclockwise means positive. So that means that we're going to start somewhere over here with some positive value for omega. What happens to the value for omega? It's gonna slow down, right? Because it was going up, but it's going slower and slower and slower. So the value, the number of radians that it is sweeping out per time starts to go down. Does that make sense? Because it's slowing down, so it's going to slow down. And what happens at the very end, or at the very top, or at the very edge before something happens? Like, what's going to happen? It's going to stop. For a long time? No, just for an instant. And then what happens?
Going in the other direction.
It starts going the other direction. So it starts off from a 0 radians per second, and it's going to start speeding up. Does that make sense? So it's going to start speeding up in the other direction. Something like that. Is that okay? Okay. Now, before we move on to alpha, have we drawn a graph like this ever before except having a V here?
Yeah.
When have we done that?
In kinematics.
In kinematics, when? Give me the example of what we saw, what we did that had this graph.
I throw a rock into the air.
I throw a rock or a frog or an anything, right? I give it some initial velocity in the upwards direction, and what happens at the very top? Velocity is 0, and then it starts to speed up going downwards. Does that make sense? So this is very, very similar, and actually, if you look at what happens to the mass, think about what happens to that mass. It's going to go up, down, just like the frog goes up, stops, and comes back down. Same thing. You see that connection? It's beautiful. It's a beautiful thing. All right, and what about this alpha graph? How do we figure out the alpha graph? It's just the derivative. I don't know what that means. Use non-calculus terms for me, please.
I don't know if I can.
Yes, you can. It's just the... How do I get from this one to this one? Slope, right? This has what kind of slope? Negative and constant. So this value is going to be negative and constant. We've seen this. We know this now, friends. Boom, it's going to look like that. Is that okay? Okay. So I really like this question for a lot of reasons. I like that we have to think about what's happening. I like that we have to think about how that's related to translational motion. And that's a big deal because the next thing we're going to talk about is the relationship between this rotational business and the translational business because we're going to have to go back and forth between them. Okay? So we're going to write a couple more things down. Here we go. There is a relationship, and it's a beautiful one. Let's think back to that definition of theta. Theta was equal to the arc length divided by the radius, right? You learned that in pre-calc or algebra at some point. You learned that it was the displacement divided by the radius. So this is like the arc length of whatever that little slice is or that sector is that you're cutting, okay? I can solve, oh, hello. I don't know why my computer's been so funny lately. I'm just going to rewrite this as x is equal to theta times r. Is that okay? Okay, so right there, boom, we know a nice relationship now between the actual displacement, the translational displacement, the one that we know and understand and can relate to very well, and the angular displacement. Okay? Is that okay with everybody? Yeah. Okay. We can take this a step further, though, now, because we know that velocity is delta x over t, right? That we know, we've known forever. Instead of writing delta x, I'm going to write delta theta times r. Actually, I'm going to write that the other way just because I like to write it backwards. So I'm going to write r times delta theta over t. Is that okay with everybody? But then Caleb says, but wait, Miss Carbeling, delta theta over t, that's just... Anybody can say it. Omega, yeah, angular velocity, right? So v is really equal to r times omega. Well, that's nice. And we can take it one step further because why not, right? Acceleration is equal to delta v over t. But wait, we know that delta v is going to be equal to r times delta omega. Is that okay? We're just going to sub in. So that means we can say this is r times delta omega over t. And then River says, but wait, Miss Carbeling. Delta omega over delta t is what?
Alpha.
Yeah. Your voice kind of cracked and went up a little higher there than normal. But yeah. No, I'm just teasing. It's all good. So A is equal to R alpha. So these three relationships here, I don't want you to freak out about them because they're really not hard to figure out. Are you with me there? They're really not hard to figure out if you know what a radian is. Okay? But these three relationships are going to get you to be able to transition between your translational velocity, your translational displacement, your translational acceleration, and the rotational equivalence. Okay? Here we go. Let's use it. Another ranking test. You guys know I love these, don't you? It's like, oh my gosh! They just keep... There are so many in here that it's going to be a beautiful thing. I actually have another book of them, too. I know, right? Don't you worry. All right. Take a moment to look over this.